Hello, I'm JW. This time I'm going to look at energy and power, and we're in this kitchen because we're going to use a demonstration involving some water, and because we can see that, and obviously we can't actually see electricity because it's really inconvenient like that. Now the basic idea is that energy is the total amount of electricity that you've used or have stored, and power is the rate at which you're actually using that electricity. So something with a low power might be something like, say, an LED lamp, say 4 watts or something. That will represent a fairly low power. And say a high power item might be, say, a kettle, which say could be rated around 3,000 watts. So that's going to use a lot more electricity once it's actually turned on. But the key thing is that's just the rate at which it's using it. The total amount you've used also depends on how long you've left it turned on for. So for example, if we turn on the kettle, say for 5 minutes, it's not going to use a huge amount, but if we turn on the LED lamp and left it on for a year continuously, it would actually use far more electricity than the kettle did, simply the fact it's turned on for an extremely long time. Now, in terms of determining the power of a particular item, pretty straightforward because it's actually printed on the item itself. So we've got here an LED lamp, and that says about 4 watts. It's actually just printed on the glass there, and the kettle there is 3,000 watts. And just have a look on the base there, we can see that it's marked 3,000 watts, and that's also equivalent to 3 kilowatts, 1 kilowatt equaling 1,000 watts. And pretty much every electrical appliance will have this marked on it somewhere, and generally it's either in watts for the lower power things or say in kilowatts for the larger ones. It's just a question of 1 watt being a fairly small unit, 1 kilowatt being 1,000 watts. Now, in terms of the rate of electricity being used, we've got this tap here. Now, in case of the, say, 4 watt LED lamp there, that is a very low power, and that would represent a very small amount of electricity being used. So that might look something like this. So water or electricity is flowing there. As you can see, it's a very small amount. It's not really doing a whole lot. And again, if we left this running for a long time, of course, a lot of water would build up there. So the rate of electricity here is very low, so this could represent the LED lamp. Now a kettle, what we have there is 3,000 watts. This is actually a huge amount more, so that would look something like this. So as you can see there, far more water is actually flowing, or far more electricity is being used. And again, if we left that running, it would fill the sink there in a very short time. So that's power, which is measured in watts or kilowatts, and that's just simply the rate at which the electricity is being used. Now, what about energy? Well, energy is the total amount used over a certain period of time, and we could represent this with this jug here, and we could say that every time the jug is filled up, that might be equivalent to being 1 unit, or some measure of how much we've used, in this case water, but the same principles would apply. Now in the case of the LED lamp, if we just turn that on, as we can see there's a very small flow of water there, or the amount of electricity being used, so that's probably say the 4 watt LED there. It will fill that jug up, but it's going to take an extremely long time, so again the amount of energy used is going to be fairly small. However, if we left it running for say 24 hours, it's going to fill that jug up many times over. Now in terms of the kettle, if we turn the kettle on, that's going to use a lot more power, and that jug is going to fill up a lot more quickly. However, the important thing about a kettle is it's only normally on for a couple of minutes. So in total, the amount of electricity we've used in terms of the energy is not necessarily going to be a vast amount. It all depends on how long it's on for. So that would represent, say, 1 unit or 1 measure. Gets there fairly quickly. Again, if it's only on for, say, a minute or 2, it's not going to add up to a huge amount. Whereas if, say, we left the LED lamp on, say, for a full year continuously, that thing will be filled over dozens of times. Now, in the real world, of course, we don't need water, but as we saw in the previous bit there, power is measured in watts, symbol W, and we also have the symbol kW, which is basically 1,000 watts. Kilo meaning 1,000, so it's just a convenient way of representing it in a more compact form if we've got things of a fairly high power. Now, in terms of energy, which is the total amount, Because this involves both the rate at which we're using it, so the watts, and also the length of time that we're actually using it for, what's generally used is watt hours, which is watts multiplied by hours, or for things like, say, an electricity bill and other things, it's more usually put down as kilowatt hours. Now that could represent 1000 watts for 1 hour, and it could only be any other combination as well, because bearing in mind it's not just that particular combination, it could just as easily be half of that, say 500 watts or 0.5 kilowatts for 2 hours, and pretty much any other combination of. So the main point is that the rate at which you're using it is completely separate from the total you're going to use, because it all depends on how long you're using it for, hence the hours part in there. You can also have things like watt seconds, so that's how many seconds it's been used, certain power rating, and so on like that, but generally watt hours or kilowatt hours are the ones that you'll normally find. And if you have a look on your electricity bill, you'll find it's measured in kilowatt hours, and that's actually what you're billed in. In the UK at the moment, that's typically around sort of 35 pence or so per kilowatt hour, and so that represents, say, a kilowatt on for 1 hour, half a kilowatt on for 2 hours, or pretty much any other combination of that. Now, the examples of the kettle that we had there, the kettle was 3000 watts, and that's also equal to 3 kilowatts. That's a small k there, both of those exactly the same. Now if we left the kettle on for 1 hour continuously, first of all the water would have boiled away and it would have gone on fire by now, but it would have cost 3 kilowatt hours, because it's 1 hour and the rate of use is 3 kilowatts. But of course that's not very realistic, because say it's more likely to be on for a few minutes. So if the kettle was on, say, for 2 minutes, the power or the rate of use is still 3 kilowatts. So to get this out of here, we need to multiply the two together. 3 kilowatts multiplied by the time. Now, if we multiply those together, we do actually get, rather than kilowatt hours, we get kilowatt minutes, which is not really what we want. So we need to just convert the minutes into an hour. Quite easy to do. There's 60 minutes in an hour. So 2 minutes is 2 divided by 60. 2 minutes out of 60. And again, we're going to multiply that by the 3 kilowatts, and then that will give us the total amount in kilowatt hours. Now this is very straightforward. If you're going to multiply these together, you're just basically multiplying the top. So 2 times 3, of course, is 6. 60 minutes, obviously, in an hour. 6 divided by 60 equals 0.1, so that's 0.1 kilowatt hours, or basically a tenth of 1 unit. So if you were paying, say, 35 pence per kilowatt hour, then the kettle being on for 2 minutes would cost you 3.5 pence. So not a huge amount, but nevertheless a noticeable figure there. And if you want to save money using a kettle, do not go and buy a new one thinking it's going to save you money, because it won't. The way to save money using a kettle is to only put in it what you actually need to heat up. Because if you put in, say, twice as much water, it would take twice as long to heat up, as in 4 minutes, and instead of costing 3.5 pence, it would cost you 7 pence, as in twice as much. So if you're filling your kettle up with, say, twice as much water as you need every single time, you're literally wasting twice as much, or using twice as much energy as you should be. That is how you reduce the amount, just by heating up what you want. Now the LED lamp we saw there, that is only 4 watts. So a very low power compared to the 3000 watt kettle, but it's the same principles that would apply. Now a LED lamp being on for a couple of minutes is not over likely. More likely it might be on for, say, a number of hours. So let's say that the 4 watt lamp, somebody left that on, say, for 6 hours. Now the calculation is exactly the same. See how much we're going to use in total. It is the two of those multiplied together. However, bearing in mind we want it in kilowatt hours generally, so you can work out how much you're paying. If we multiply these two together directly, we would actually get watt hours, because it's watts multiplied by hours. So 6 times 4 would be 24, and that would actually be watt hours. To get that to kilowatt hours, it's just divide by 1000. As we saw earlier, 1 kilowatt is 1000 watts. So in this case, that would equal 0.024 kilowatt hours. And again, if that was at 35 pence per unit, 35 multiplied by 0.024 actually comes out to 0.84 pence. So even though it's been on for 6 hours, the fact that it's only a tiny 4 watts means it costs less than 1 penny to actually operate for that time, whereas previously the kettle, although it was only on for 2 minutes, actually cost 3.5 pence, simply because the rate at which it used electricity was of course dramatically larger. However, if we left this on, say in the kitchen there, if we left it on for the entire year, it would have actually cost a pretty significant amount. Just see what that actually would be. Still 4 watts. Instead of 6 hours, it would actually have been 8,760 hours, which is a full year's worth of hours. That would be 35,040 watt hours, or divide by 1,000, obviously that's around 35 kilowatt hours. And if you multiply those two together, 35 pence, 35 kilowatt hours, it's actually around £12 if you left that thing on for an entire year continuously. So although it's low power, don't be fooled into thinking it's going to be cheap to run, because again it depends on how long it's turned on for, and even low power things left on for a year can add up to fairly significant amounts. Now all of that actually applies to most other fuels as well, in fact all other fuels. So if you look on your gas bill, you'll notice that's also in kilowatt hours. Gas isn't actually measured in kilowatt hours directly, but it is converted into those, basically so you can do a comparison between, say, gas and electricity. And you can actually apply the same to anything else. So if you have oil, for example, that's generally measured in litres, but then it's a question of how many kilowatt hours there are per litre, and again it can be priced that way. And even things like petrol or gasoline if you're in America, and diesel and whatever else, again you're not going to buy that in litres or gallons or whatever, but again you just need to find out how many kilowatt hours there are, say, per litre or per gallon or whatever, and again it's all the same thing, it's just a unit of energy. It doesn't actually matter whether it's electricity or pretty much anything else. Now the other area you may see watt hours and kilowatt hours is in batteries, particularly in things like laptops and electric vehicles. Now, because batteries are a store of energy, the amount of energy a battery can contain is either going to be in watt hours or kilowatt hours, again depending on the size of the battery. And these are exactly the same as the ones you would buy from your electricity supplier. So if you have, say, a battery in an electric vehicle, it might have a capacity of, say, 50 kilowatt hours. And if you wanted to charge that fully from empty, you would need to obtain 50 kilowatt hours of electricity and shove that in there. And of course that will take a fairly long time. And to charge that up, if you wanted to charge that literally from 0 to the full 50 kilowatt hours, and it was 35 pence a unit, then the total amount is going to be 50 times 35 pence, which would cost you around £17.50. Now in reality it would actually cost a bit more, because charging a battery is not 100% efficient. There are some losses, loss to heat and whatever, but assuming it was, then it would be around £17.50 to take that electricity from the electricity supply and then store it in the battery for later use. And the same applies to most other batteries. You'll see watt hours quite often in things like laptop batteries or phone batteries. Generally, of course, those are a lot smaller capacity than obviously an electric vehicle. You'll also see on things like laptops, you will have obviously a rating of power in watts, and you'll see it on the back, say sort of 5 watts or 10 watts or whatever else, depending on the rating of it. So a phone might be sort of 5-10 watts or something. Laptops can, of course, be quite a lot more. And in the case of an electric vehicle, it will have an electric motor in it, and again that is rated in watts, or more commonly kilowatts. So for example, you might have, say, a vehicle with a 50 kilowatt hour battery, as in the amount of energy it's stored inside, and the motor in that vehicle may be rated, say, to 100 kilowatts. Obviously that's quite a lot compared to other things, but then shifting a 2-ton metal box down the road does actually require a very substantial amount of power. Now, unlike the kettle, which basically uses whatever it says on the label, and for that matter the LED lamp there, when it comes to things like motors and electronic devices like laptops, computers and all that stuff, what's printed on the label is actually the maximum power that it could use. However, a lot of the time it's going to use considerably less. And for example, in the car, the motor could use 100 kilowatts, and that would represent if you were going uphill, fully laden with all the passengers in there and loads of luggage and pulling some massive trailer and a caravan, and you were ramming your foot right down on the floor, then in that situation it would obviously use the 100 kilowatts. But of course, if there's only like 1 or 2 people in it and you just drive along the flat, it would use considerably less. And the same thing really with phones and laptops or whatever. If you just turn the phone on and just have a look at an email or something, well, it's going to use very little. On the other hand, if you've got some gaming laptop and you're playing some game there with full resolution video at 60 frames a second or whatever else, and the sound was blaring out, it's going to use considerably more. So for these types of devices, and in fact that applies to almost anything apart from basic stuff like a light and a kettle, this is just the maximum, so you can't really establish the amount it's going to use over a period of time without actually measuring it directly. As I say, it will vary depending on what you're doing with the device. In terms of how long batteries will last, that is actually fairly straightforward. We'll take the example of the electric vehicle. Now, if we use the full 100 kilowatts continuously, which is not realistic in a vehicle, but if you did, because we've only got 50 kilowatt hours, essentially that would run for half an hour, or in other words 30 minutes, and that's because 100 times a half is 50 kilowatt hours. So it's the same as before, it's just multiply the two together. Kilowatts multiplied by hours is kilowatt hours. However, say in reality you're not going to be using the 400 kilowatts very often or even at all. So in practice, of course, you can obviously drive for a lot longer than 30 minutes before the battery needs to be recharged. So if it is something that uses a constant power, say like a kettle or whatever, then it's relatively easy. But of course, in the case of a car or laptop or whatever else, it's, you need to really measure it directly rather than just doing the calculation. But as an example there, if we took the 50 kilowatt hour car battery and we connected a load to it, and you can do this on some vehicles now, if we plugged our 3 kilowatt kettle into the battery, or even a 3 kilowatt electric fire, and we can see how long we could actually run that for, and that would be 50 divided by the 3, which would be the kettle, and if we use the whole capacity of that, 50 divided by 3 would be around 16.6 hours, and that's an awfully long time to run a kettle. It's also an awfully long time to run a 3 kilowatt electric heater, and it does illustrate the massive amount of energy that's actually stored inside vehicle batteries. And conversely, if it was a lower power, if say a 1 kilowatt kettle or 1 kilowatt heater, we could obviously run that for 50 hours, or in fact more than 2 days continuously. Now the other just final point here, particularly with batteries, is that you'll see a lot of batteries, particularly lead acid things and like AA's and that kind of stuff, are actually measured in amp hours, or in some cases a milliamp hours, which is 1,000 times smaller. This was generally done, particularly for older ones, where the voltage of the battery was constant over time. And for example, a 12 volt lead acid battery, those generally are marked in amp hours on the side. You can convert this to watt hours very easily. It's just amp hours multiplied by voltage, and that will give you watt hours. That's capital W, obviously. So for example, if I had a 12 volt lead acid battery and it was an 80 amp hour rating, then it's just those two multiplied together. 12 times 80 would equal 960, and that would be 960 watt hours, or you could also call that 0.96 kilowatt hours, or roughly just under 1 kilowatt hour. You can also do this with other batteries, like say lithium batteries. However, you need to be careful of those because it's the voltage which really matters. And if you buy a lot of those power banks, and no doubt seen those ones output say 5 volts, they're quite often marked in amp hours, or in many cases milliamp hours. So for example, a moderate sized one could be marked as 20,000 milliamp hours. That's actually the same as 20 amp hours, because just divide by 1,000. Now those output 5 volts. However, crucially, on virtually all of them, that is not the rating of the output voltage, it's the rating of the battery inside, and that's going to be some kind of lithium battery, and they're usually at the actual sort of nominal voltage of that, which is around 3.6 volts. So again, it's 20 multiplied by the voltage of 3.6, so that would give you a total of around 72 watt hours. not multiplying up by 5, which would be around 100. And of course, if you've seen a lot of these on the usual dubious selling places, a lot of these things are grossly exaggerated and some of the figures are just absolute nonsense, so obviously beware of those. So in summary then, the rate of electricity used is watts, or in larger items kilowatts, which is just 1,000 times larger. But the total amount of electricity you've used and what you're either going to be storing in a battery or you're going to be billed from your electricity supplier is the rate in watts multiplied by how long it's been on for, as in the time. So watts multiplied by hours gives you watt hours, or more usually kilowatt hours, which is 1,000 times greater. So just because you've got, say, a kettle which might use 3,000 watts, how much it costs to run you can't tell. It's how long it's turned on for as well as the power rating which actually matters. Now next time I have a look at certain things and how you can determine how much energy they do actually use, but that's in the next time video, and until then, thanks for watching.